I wanted to recall a bit the notation of last time because I understand it could be a lot of notations. So it's good to just like go through them once more. So we defined board 1 is our category, is our source category. Is a category of bordered surfaces. Bordered surfaces, it's a smooth, oriented, compact, two-dimensional manifold with oriented boundaries. And moreover, this 1 here stands for the fact that every connected component has exactly one disagreeing oriented boundary. So for every connected component, you will find exactly one distinguished boundary that has the opposite orientation. And the morphisms in this category are different morphisms that are orientation preserving up to isotopy. Then we have this P sigma. So I look at the bordered surfaces sigma, and I take the set of embedded pair of bands up to homotopy. And I also want this subscript D. What is D? So I take any D, which could be the empty set or some connected component of the positive oriented boundary of sigma, one of the two. And then I take the set of embedded pair of bands such that the intersection between the image of the positive oriented boundary of P and of sigma is exactly D. So you have to think it like that. You have D here and the pair of bands here, and this is inside your surface. So sigma is something like that, maybe with some genus, and you have something's already wrong. Okay, like this. And here I will have like some genus. So this is the pair of bands that is embedded, has like a negative boundary here, positive boundary here. This is D. D is also a positive boundary that is shared by the surface sigma. So on the right, I write only positively oriented boundaries, and on the left, I always write the unique negatively oriented percolator component. And you see that the only shared boundary is, in the positive ones, is D. Okay, and then we want S sigma to be the set of multicurves, and with this hat we indicate the closed ones, and with the circle we indicate the same two sets, but then we want to avoid to have connected component in the multicurves which are parallel to the boundaries. So with these circles, we don't want that if this is the boundary of the surface, we have like a component of the multicurve which is like that. This we don't want in the last key. Okay? And then last time we also saw like what are the axioms that are needed for the definition of the geometric recursion formula. So the first thing that we needed is this functor E, which goes from board 1, which is that category, to pro V, which was the category of these kind of objects in which you have two sets of indices. First you have, like for each surface, you have a set I. So when I indicate this bullet here, it means that when you evaluate E in a bordered surfaces, then you would have the correspondent index I sigma, right? So this is the bullet. And moreover, you have another set, which is AI, where I, this index is bullet. And for each kind of indices, you have a sequence of this vector spaces VI, which has like a projective limit to some vector space V, and this also sequence of semi-norms. And moreover, the morph is in this category set bounded objects to bounded objects. This means that first you define your, so like this, would be like a soup among all the alpha in a I, bullet of your semi-norm, and then you look at the objects which have this norm finite for all I. Yeah? And then the morphism, we are saying that the definition is that they send bounded objects to bounded objects. Then we must have a union, which is a map from E sigma 1 and E sigma 2 to sigma E of sigma 1 union sigma 2 with compatibility conditions, and moreover, what we call vacuum, the fact that E of the empty border surface is just the field K, which is usually C or R. And moreover, we want the excision axiom, which is very important, which says that if the Euler characteristic of sigma is smaller or equal than -2, so it has enough pair of bands, then you want to be able to cut. So for every homotopy class of a pair of band P in P sigma, then you want to be able to cut the bands, and you want to have such a map theta P that goes from E of the bands times E of the surface minus the bands to E of sigma. And we call this a pre-target theory. And in order to make it a target theory, we need other 3 axioms. I have to be careful about shape. Okay, let's do that. That's sufficient. So we moreover need the notion of length. Like that one. So if you take it all together, these are the axioms needed for your target theory. And you need this notion of length, Li alpha, same notation. And you want these 3 axioms. The first is the lower bound. So for every index I in your I of sigma, there must exist like a small delta I, such that if you take all this length among all the alpha in the AI and all the gamma, which must be closed multi-curves without components which are parallel to boundaries, then you want them to be bounded from below. And moreover, you want polynomial growth, meaning that every time that you fix again an index I, you want to look at the number of multi-curves which are not necessarily closed, but they must again not have components parallel to boundaries. And you look at their length. You want to count how many of them are shorter than lambda, and this should grow as lambda to some constant di times another constant mi. And this di should be the same for all the alpha. So mi and di are uniform in alpha. And moreover, you want, the last one is the small pair of bands, which says that for every I in this index here, there must exist again some constant qi, which is again the same for all the alphas. And every time that you pick a b as connector component of the positive oriented boundaries, so you have again your sigma with all your, you have a negative, you have plus plus plus, you have some genus. B is one of those guys, one of these. And then you want to count how many times it happens the following. Then you have a pair of bands embedded in sigma, such that, roughly speaking, this is small, and these two are big. In particular, the sum of those two is bigger than this one. So basically, you want this to be big most of the times, and only finitely many times you want that the sum of these two is bigger than that. And for this pair of bands, it's the same. This time you have gamma 1 and gamma 2. And now you're asking how many times the sum of these two is smaller than this. You want this to happen only finitely many times. And also you want to control it with a constant that is the same for all alpha. So the number of these pair of bands in which the length of B1, which is the only negative oriented boundary, is bigger or equal than the sum of the other two, can happen at most qi times. So these are a lot of axioms, but if you want a mnemonic way to remember this axiom, you can think of a target theory as a kid of about 5 years old. because you see it's not too small. It will grow, but not exponentially, and we're still able to wear small pair of pants. Now, so this was about our target theory E, and now we want to speak about the initial conditions for the recursions, which are this A, B, C, and D. So we've seen last time we had these elements in the target category, A, B, C, and D. A, B, C are relative to pair of pants, meaning that they live in the image of the pair of pants with respect to the factor E, and A and C are invariant with respect to the macroclass group. And you want A and D to be bounded elements. So this norm with the double slash is finite for each I, for A and for D. And for B and from C, you are requiring that they satisfy a certain condition on the decay. So I wrote down the condition only for B, and for C it's just the same. So for B, it reads the following. You take any border surfaces, which is connected, and you take any homotopy class pair of pants. And then you take any pair of indices in the product of EP times E surface minus P. And you take any K, so this is K, in the index of sigma, such that this is smaller of some like order and preserving map. And you want that, so this is the important part, you want that it exists some constant Sk, which must be greater, strictly greater than dk. And dk is the same dk that is called the I there. So it's the polynomial growth constant. Such that there exists some constant m, I, j, k, such that for every alpha in the set relative to sigma, and for every positively oriented B, and for every pair of pants that shares only B as positively oriented boundary, and for every V that is in the image of the surface minus the pair of pants invariant with respect to the macroclass group, then you want that the semi-norm of this object, what is this? This is, you take your B, because it's a decay condition on B, so you should have B somewhere, and this is the B relative to the boundary V, and you glue it with respect to V. So V, it's an element in your surface minus the pair of pants. And B is relative to a pair of pants. So you glue them together, you find something that lives in the image of your surface. And this is relative to the indices AJK. Then you take the semi-norm K alpha. You want this to be bounded by the following thing. You just have a constant that depends on IJK. You have the norm J of your element V, which is this one. And then you want that this goes like 1 over 1 plus something to the power sk, which sk must be greater than this polynomial growth constant. And this thing is basically very similar to what is written here in a small pair of pants. You take the length of gamma minus the length of B1 minus the length of B, and then you take this parenthesis plus, where this parenthesis plus is just the maximum between 0 and the argument. So this thing would be 0 every time that this guy is smaller than 0, and would be this expression every time that this expression is greater than 0. Okay, and so now the main claim of the geometric recursion is that if you, these are everything you need, basically. So if you take a target theory with these axioms and you take admissible initial data, then you can define the geometric recursion in this way. You take admissible ABCD, you take E target theory, you define omega of empty to be 1, because we know from the vacuum, which is over there, that E of the vacuum is our field K, so we can always pick 1. And then you use the initial data in the following way. You take omega of the pair of pants to be A of that pair of pants, you take omega of the torus to be d of that torus. You take omega of something disconnected to be the formal sum of omega of each component. And now you're only left to define what is omega of something connected with Euler characteristic smaller or equal than 2, minus 2. Okay? Because for Euler characteristic equal to minus 2, you only have pair of pairs and toroid with one boundary. And with Euler characteristic like higher than that, you don't need anything. So you want only to define what is Euler characteristic lower than that. So equal to minus 1, because it's smaller or equal than things. Okay, and so you define it like that. You take the formal sum over all the positively oriented boundary of sigma. Sigma is the element that you're defining. Then you take the sum over all p's in PD sigma, and then you glue, with respect to p, your initial data b and your sigma of e minus p. But then also you have another possibility. You can also have a pair of pairs which does not share any positive oriented boundary with sigma. And then you glue it together with this one, but then you divide by 1/2 because this pair of pairs is symmetric. You have this gamma, so it's this case, you have gamma 1 and gamma 2, so you just divide by 1/2 to take care of this symmetry. And the theorem is that this formula here is well defined, even if these are infinite sums. And moreover that the function associating to sigma, omega of sigma, is functorial in the surfaces, in the border surfaces, and moreover that omega sigma are mapping class group invariant. But this is more or less obvious because the mapping class group is just shuffling summands. So this is the easy part. So the complicated part actually is to see that this is well defined, namely that these sums converge. And this is what we're going to do. Do you have questions so far? Because it's a lot of stuff. Okay, I think I should draw some pictures about those, just to make it a little bit clear.
Maybe I have a question, maybe it was from last week. So the omega, how can I think of it? It's like an upgraded version of what E was, or it's completely not like that?
Omega of sigma lives in E of sigma.
Okay.
It's an element of E sigma. And E sigma, you can think of it as like some infinitely dimensional vector space.
Yeah.
So what we're going to do is first to give an idea of the proof, and then we're going to see like an example of target theory, so like a concrete one, in which E of sigma will be continuous function on the Teichmüller of sigma. So you can think of omega sigma in that case as a continuous function f from the Teichmüller to your favorite C or R. Your favorite field, if your favorite field is C or R. Okay, I'm going to draw some pictures and hopefully it will be a little bit more concrete. So, you basically have, in this formula, you have three possible cases. There is the case in which you're gluing with respect to B, and then your surface sigma should look something like that. So here you have some genus, and here you have just a pair of terms, and the data that this piece is carrying is omega of sigma minus a pair of times P, and the information that you are using here is dP of pair of times P, where P is this pair of times P. D1 is your negative oriented boundary. This is positive, 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 positive. So what we are doing, like in the first summand, is sigma P corresponds to gluing the information coming from this piece and this piece. And when you're doing with respect to C, you have two possible scenarios. One is you still have D1 here, negatively oriented, and you have so I'm drawing the pair of pens in the opposite way of what I wrote here, because like this axiom makes me think that like most of the times you will have this scenario, which this is very big with respect to the others. So this will be my gamma 1, my gamma 2, and only two things can happen. Either when I cut away this pair of pens, the surface stays connected or not. So if it stays connected, then I will have something like that. And here I have my omega of E minus P, and here I have my CP. This is my pair of pens P. And we need another big class of this. And otherwise, you can guess what the other one should be. Yeah, I'm not drawing it correctly because I only have. Maybe I should have another one. Okay. And here I have my omega E minus P1 first component, and here we'll have omega of E minus P second component, and that's okay because we said that when we have omega of something disconnected, it's just the formal sum of the two. This should be my C. And also we've seen last time that these are orbits with respect to the multicast group that preserves the boundary. And basically, these are all the possible orbits that we have. Here we'll have one orbit per B. And here we'll have just these two possible cases. Okay. Maybe you want to show this. Okay, now we're going to give like an idea of the proof. And the proof will go by induction on the Euler characteristic. So the first case is when the Euler characteristic is equal to -1. It's already done because A and D are only like the curve pens and the torus with one boundary are the only possible cases, and you know that they are bounded already because you require boundedness here, and also they are not grouping valid. And then the disconnected ones are also okay. So basically you just need to check that those sums are convergent in all the seminorms. By admissibility. Now I want induction. Right. So suppose that it holds for all uncharacteristic strictly equal than this one, and then take sigma such that the characteristic is by 0. And first, observe that basically, you first look at, okay, I will do only the case for C, because the case for B is just the same. And the first, you have to observe that this omega p of Cp omega, this is theta p of Cp and omega sigma minus p. It does not depend on the representative chosen in the homotopy class, but this is okay because of the Funtorial properties of E and of the Green maps. And then you just care about the fact that you have an infinite sum, and you need to somehow to tame it with these axioms over here. So this is the most interesting part, I think, how these axioms intervene in taming the sum. So before doing that, I want to recall, I'm not sure last time we did it, or maybe we didn't. I don't think so. I want to give an alternative description of P sigma, which goes like this. You take your sigma here, so you have positive oriented boundary and the negative one that we always call V1. Then you have some genes. And then I want to take some curve C that starts from a point in here and reaches a point in here. This is my V. So, for instance, you can go like this. It's like a C. Okay, and then I want to consider the following gamma C, which is a curve that is defined in this way. Like follow C in this direction, from here to B, then go around B, then follow back C, and then go around V1. Yeah, so you start from here, you follow, then you go around it, then you follow back, and then you go around it. Yeah. Okay, then you consider it's a homotopy class, so you have to think that you have something like this. And somehow you cut along this is your gamma C. You cut along it, and you get two components. You consider the component that contains B and BI, and you get a pair of bands. You get a pair of bands, and you look at the three boundaries that you have. So one boundary will be B1, because it's completely included in the pair of bands. One boundary will be B, and the third boundary will be the entire gamma C, if you think about it. Like, probably it's easier if you think about it, gamma C like expands from C and goes like far away. Yeah. So you get a pair of bands with boundary, which has B, B1, and gamma C. So now the description of P sigma is as follows. P sigma empty, so it was the one that does not have any, maybe I should do it first, sorry. P sigma of B is in bijection between simple curves C in sigma that go from B, from a point in B to a point in B1 relative to the boundary. So the only thing that I didn't say is that you can take a simple representative in the homotopy class of gamma C. So, and it's actually a bijection. And when you do, you can do the same with, not with a PB sigma, but with P empty of sigma. And you will have a bijection between, again, simple curves C in sigma. This time that you go from a point in B to a point in B again. In B.
B1.
From a point in B1 to a point in B1. Thank you. Also relative to the boundary. So instead, what your C prime would look like is something like that. You start from here, you do something non-trivial or something trivial as well, and then you end up with your C prime, and then you can do the same. And in this way, you will end up with a pair of pens with boundary gamma C prime, and also, no, I'm sorry, you end up with something that has like a B1 and also gamma C1 and gamma C2. How do you get this gamma C1 and gamma C2? You take the curve that from here go around this, and then just fill this gap, and then you take the other one. You start from here, you go around, and you take the other direction. And then you take the homotopy class of that, simple representative, and this would be your new boundaries, which correspond to this gamma 1 and gamma 2.
Okay. I'm sorry, in this construction, do you have to fix it in the boundaries?
It's relative to the boundary. See? From a point in B to a point in B1, relative to the boundary.
Okay, so you fix the boundary, you fix one point, and then...
Yeah, it means like you portioned out with the, it doesn't matter where you pick it. Yeah. Okay. So to me, it helps to think about it, to think about P sigma in this way, because I mean, I'm completely inexperienced in Teichmüller theory. So for me, it helps to see that this sum is infinite, because if you think that this is now in bijection with this kind of curves, then it's very easy to understand why they can be infinite, because you can, like, for instance, go inside a hole and then go inside the other one and take several times around, and then you can mess up, like, between the border and one of the holes. And you can do many things, many different things. They will all be homotopy inequivalent, and you have infinitely many of them. So I don't know which one is for you the easiest, but this is the one for me. Okay. Okay, so now I want to take an orbit O in the active sigma, so one of the two above. And then, because of the functoriality property of E and the grid maps, of E and theta of E, you can pick sets I, O, because depend on this orbit 1, and I, O, 2, and some element E, O. And I will tell you now what I do. So this one, you want it to be canonically identified with IP for all the P in O. And this one you want to be identified to I of sigma minus P. And this one you want to be canonically isomorphic to E of sigma minus P, also for each P. So basically you look at the orbit, one of the two to the right, because we're doing the C case. So pick one orbit, you fix it, and then you look at all the elements inside this orbit. There will be a homotopy class of pair of bands, and each of them will be associated to an index, because the target category is this pro P, which has all these indices I. And then, because you know that each of these elements in the orbit of the mapping class group that fixes the boundary, then like these indices as well will be identified by the elements of the group. So you just pick one index for each of these, one for your pair of bands, one for the surface minus the pair of bands, and also you pick an element in here. And so this allows you to think that all these E omega or E minus P are like identified with omega O for each pair of bands in the orbit. And then you write down your C decay. So now you will have the sum over P in O, and you want to take the norm, ij in P, and you want to glue Cp together with omega E minus P. Alpha K. And you know already that this is bounded by a constant times omega O J. So I just take this condition here, the C decay with C instead of V, and I take as V this element. And I plug it inside the definition, the axiom, and then I have the sum P in O, and I have 1 divided by 1 plus length K alpha, gamma 1 plus length K alpha, gamma 2 minus L K alpha of P1 plus, sorry, you don't see it, and then I take everything to the power sk. So this plus is this plus, which means that I take always the maximum between what is inside and 0. And then, so it's just a constant. And then you want to look at this expression. So this is the only thing that can mess up your convergence, your absolute convergence. You want to take this sum. And now you observe the following. Of course, what is dangerous is that when this denominator is close to 1, right? And of course you're worried about how many times this guy can be 0. But how many times this guy can be 0? We know that now by the small curve bands, this can happen at most qk times. So this guy would be 1 divided by 1 to the power sk plus 1 divided by 1 to the power sk. And this can happen at most qk times. And plus, you have something else. So maybe I should write the axioms when we use them. So this is C decay. We used it already. And now we're using small curve band. Here. And now we want to control when this is not 0. Okay? But now we want to use the polynomial growth and excite it a little bit. Because Polynomial growth tells you that you want to count how many times the length of gamma can be smaller than lambda. And this will have a polynomial growth with dk in this case, which is strictly smaller than sk. But then you can notice that also the fact that the sum of these two lengths will have the same polynomial growth if you write it out. And so you will have a number of summands that grows like m, k, lambda, dk, but then it will be divided by something that is to the power sk. And this will grow faster than this one. So you can tail this guy. So this is basically how you deal with that sum. And then what you proved is that this sum is absolutely convergent for each k and each alpha. And therefore, you can take projective limit and then you can show now that. So this guy will converge to some element in k of sigma for each k. And then you know that this element here that I call WO of I take k that is defined to be the support of this smaller than infinity, so it will belong to actually to ek sigma bounded elements, and this is a condition that I need. And moreover, for the fact that all the maps involved, like the gluing ones and E, are compatible with the projective limits, then you can absorb this I and J, and so this element here only depends on K, and you have to repeat the same procedure with the sum with the other orbits, but that the proof is just the same, and then you repeat the same procedure with the sum over gluings over B. And then the only thing left is to prove the functoriality of the assignment, that sigma goes to omega of sigma. But I don't want to do that because I think this was like the most interesting part. So this is the idea of the proof. There are a few more details, but. And then the fact that this mapping Planck group invariant is automatic by the fact that in the formula you sum over all possible cases, and then the mapping Planck group just shuffle them. Sorry?
What is small omega?
It converges, so this guy converges to some element in ek of sigma that I call omega. Oh. Okay, so now the idea would be to erase all the voids on the right and talk about the case in which of continuous functions are kept in space. So basically what we want to do is to prove that all the axioms, one by one, hold. So I think of the Teichmüller space as either the set of hyperbolic matrix on sigma, where the boundaries are geodesics, and then modulo decomorphism, which are isotropic in identity, or another way to think about it, equivalence classes. Morphism from my sigma to S, some Riemann surface. Where I have to define what does it mean to be equivalent. So E1 and E2 are equivalent if and only if there exists some bi-holomorphism from S1 to S2, such that mu2, the minus one composed with bi-holomorphism composed with mu1 is isotropic to the identity on C. And then if you take a stable surface, then you have the action of the mapping class group that fixes the boundaries on the Teichmüller space. This action is free and properly discontinuous. You get a portion that is the moduli space. And on this guy, we have the action of the mapping class group that commutes the boundaries. And then we will also need Teichmüller. Here the notation is a bit, I don't know, it's like bold. This would be the pointed Teichmüller space, and is defined as the same plus the data of a vector O, which is OB, one per connected component of the positively oriented boundaries. So basically you have your sigma plus plus plus, and you have one marked point, O1, O2, O3 for each of these. And then the condition is that with the definition, with the second definition, when you do this, this must be again isotropic to the identity, but then also should be the identity on O all the way along the isotropy. And moreover, you have this guy, which is the group of the centrists. And this X here. And if you take the quotient, we call it Teichmüller with bold E and this tilde. It's the quotient between the two.
So this is just the exists on the boundary curves?
Yes. And then this guy is smooth of dimension 60 minus 6 plus 4n. So this guy is dimension dimension 6g minus 6 plus 3n. So this is just dimension n more than the other one. And for instance, okay, let's make an example. If I take Teichmüller of the period bands, this will be just R positive to the power 3. If I take Teichmüller with this bold P, meaning that I also have these mark points on the sorry, this I don't want positive ones. I want all of them. This will be R bigger than 0 times R to the power 3. Because you can mark one point in each of the 3 boundaries, and then you can basically rotate them the way you like. So you have like an entire new real line per boundary. But if you quotient with respect to the bandwidth, so you take a tilde, this would be R positive times U of 1 or S1 to the power 3. So just quotient by Z, basically. You have like just this point can be on one copy of S1, and then if you go to the next one, that's modulo the bandwidth that you quotient out with. Okay, and now we see that this notion of length that we have there, it comes naturally in this case from your hyperbolic structures that allows you to measure lengths. Maybe I should wait. Okay. So I take an element of the Teichmüller, my hyperbolic metric, and then if I have my surface, and I take some gamma, and then the thing is, if I want gamma to be simple and closed, then it exists and is unique. As short as in the homotopy class of gamma. And then I take this as definition of length of gamma with respect to the hyperbolic structure. And then if you have the length of the multicurve, it's just the sum of the length of the component. Okay, now I want to take all simple closed curves in sigma, and then I want to take all their length. And I want to order them with everything with respect to a fixed element sigma. So I order them, and I will have L sigma 1, smaller equal than L sigma 2, smaller equal than sigma 3, and so on. And this will be originally 0. And I call this will be the definition of my systole of sigma. So I call it systole, the smallest among all of them. So I want to take sigma stable border. Stable, maybe I didn't say it yet, but it just means that if every component of sigma is stable, meaning that I don't have things like this one, like this one, like this one, everything. So any of these components should be one of those. And a sphere. Okay, and then you want to pick sigma, it's not called sigma, gamma prime, which are both sigma geodesics. You also want to they intersect transversally. And you have two possibilities. That's the joint. One is sigma belongs to boundary. This gamma, not sigma. And the other one is if gamma is inside the interior. And you want them to intersect transversely, so this would do something like that. Or maybe I should draw this like that. And in this case, it would be something like that. It's my gamma prime. So in this case, gamma prime is so, and gamma is inside the interior, and in this case, gamma is inside the bottom. Okay, what color lemma helped me? It's an estimate of the length of the not the ratio, but somehow like how the length of these two interact. And the statement is that in this case, we have hyperbolic sine of the length of gamma divided by 2, hyperbolic sine, the length of gamma prime divided by 2 is greater than 1. And in this case, we have basically the same thing, but because here you have like more than half of it, then you don't have to divide by 2 again. So this is what color lemma says. And okay, for me it's very nice that hyperbolic sign up here for many reasons. One is that later we're going to see some estimates that also will involve hyperbolic functions, and also because Miyazaki recursion has used these functions, and we're going to get there, but in the next talk, not this. Okay, so this we will use later on. Just put it up. So I now want to take as a target here my E from everyone. Before I had pro v, and now I want to do the following. I want to take t tilde epsilon of bullet of semi-norm that depends on epsilon and k. Then I want to take over k in the compact sets of t tilde epsilon bullet, and I'm going to define this guy now. And then I want to take an I in R.
And it should be the same order on that. You need a vector space, right?
Yes, thanks. So, okay, let me define the linguistic one. T tilde of epsilon of sigma. So when I use this bullet as before, it means that every time that you evaluate A in sigma, sigma will come here. Okay? And this guy is essentially all the sigmas in T tilde of sigma, such that the systole of sigma is greater or equal than epsilon, and moreover, the length according to C of P is also greater or equal than epsilon for every P positively oriented boundary. So the systole is just the smallest. What was it? I just erased it. It's the smallest of all these lengths of simple closed curves according to sigma, and then I also want the boundaries not to be too small, and I also want all these internal closed simple curves not to be too small. Basically, I'm afraid of like degeneration. And then you want to define. So I just want to compare a little bit the notations with the pro v that we had there. So in what we called first I now corresponds to epsilon, and epsilon is an element of R bigger than 0. So basically, what you're doing is that you're taking this to be R greater than 0 for each sigma. And moreover, instead of alpha, you're taking k, which is a compact in Teichmüller. Well, and it depends on epsilon, which is I, so it has the same dependence. Everything that you call the vector v before now is a function from t tilde epsilon to your favorite field k, and what you called before this norm I is now the norm of f. Depends on epsilon, which will be the sup of f k epsilon inside oh sorry, I have to do this one first. Okay, let me do this one first. First you want I alpha, and this would be I alpha, and this would take epsilon. And this would be the sup among the norm of f of sigma, which is taking k, and you want all the sigma in the compact k, which is in a space that is intersected by epsilon. So this quantity also depends on epsilon, and then you take this I is just the sup of f k epsilon. Here, and this is the sup of f of sigma, where sigma is in the whole thing still intersected by epsilon. And instead of these guys, you have continuous functions on and what you before called L alpha I is now L k epsilon, which is the minimum between L sigma gamma among all the sigma in the compact plane. So this is again the complete dictionary. Between the two cases. And then you see basically that the lower bound condition is immediately satisfied on each of the t tilde epsilon by definition. And for me, this is the main reason why they're using this projective limit approach, because on each of them the lower bound is satisfied, and on the projective limit, if you remove the epsilon, it's not. So you want to avoid this shrinking, and yeah. So this is more or less by definition. And what happens with the polynomial growth instead? The polynomial growth axiom for this case, it's a result of Miyazakani, but then adapted a little bit. So now we see how.
Danilo, question. Why do you have to take these two indices? It's like repeating itself, because you pick a compact set in Teichmüller space, it's always bounded from 0 to definition. So there's a kind of redundancy between epsilon and k. K, if you pick a compact set, it's already registered at that time. So there is sort of
Redundancy, you mean that is not necessary?
I don't know. That's why my question: why do you need the epsilon and k in this situation?
I think you need k to properly define this norm of v, I with double slash, but now you claim that you don't really need it. Or
I would assume that k is enough.
k is?
K is enough. Yeah.
But how do you, for example, guarantee the existence of this soup? You don't have compact sets. No? Okay. Maybe we can discuss it.
We need the notion of boundedness here, and these epsilon guarantees this strength of boundedness. You don't have really a norm. The limit of the norm of the I, it's not really a norm. It can be infinity.
How do you define this one? Without k?
No, k is needed. Epsilon.
But epsilon you need it for these spaces to satisfy a lower bound.
You said that if you define k, the k you could define this tau here epsilon sigma with that epsilon by taking things the shortest length. This is the length of over a quarter instead of
But the fact that you need twice compactness.
This bit of present role maybe in the other two aspects.
In which axiom?
In the other two, maybe polynomial growth.
not in the polynomial graph, but the pair of bands.
So that the system, in principle, could it be parallel to the boundaries, or is it always not parallel to the boundaries?
We take simple closed curves, but it can be. I think you're not excluding that.
No, then your definition of T sigma to that side is broken from the word in yellow. You assume that also on the boundary it's bigger than that side. If you assume this is very difficult to find second condition is very difficult to understand.
No, okay, you're right. So I think that when I order them, it's only in the S sigma not, meaning like only in the inside. Yes.
That's fine.
Yeah, exactly.
What you were saying would take care of the system being bigger than epsilon.
Yeah, that's for sure, yeah.
Okay, but wouldn't guarantee about the boundary.
Sure.
The systole is only in the inside, not on the boundary. Okay. I'm going to erase this. Because I would like to make a board that is like symmetric to that one. No, sorry, actually the lower bound I should have written the So now the lines in this case they are written by structures. The lower bound is automatic. On each of these T tilde. And polynomial graph. As follows. So there is a result of the Mirtakani that is saying that for every epsilon bigger than 0, it exists some constant g and epsilon, where g is the genus of my surface and n is the number of boundaries, so it's fixed, stable, ordered surface, such that for every element in the Teichmüller space and for every L greater than 0, n sigma L, which is defined to be the number of gamma sigma geodesics multicurves, such that the length measured with sigma smaller or equal than L. This is bounded by N, G, and epsilon. here I want the product of 1 over length of sigma of gamma, and I'm taking the product over all the gamma which are closed in sigma, and they have no components parallel to the boundary, such that their length is smaller or equal than epsilon, and I take L to the power 6g minus 6 plus 2m. And sorry, so this is when sigma has n punctures, meaning that the length of boundaries is equal to 0, and this is here on yes again. But of course, this is not exactly what we need, because we want to work with bordered surfaces, and we want to transform the punctures into boundaries which have like positive lengths, and we want to see if some similar result still holds true. So we want to adapt this for boundaries, and there is a result of Allier that says that it used the color lemma and says the same. That whenever you have sigma, you can find another sigma tilde such that the systole of sigma tilde is greater or equal than the minimum between the systole of sigma and twice the logarithm of 1 plus square root of 2. Because why not? And moreover, so this is the first condition. Second condition is that the length of sigma tilde I smaller or equal than length of sigma I for each I. These are the lengths that we ordered before, such that the first one is the systole. And the third one is that the length of sigma tilde of the boundary is strictly smaller than the length of the boundary that measures with sigma. And moreover, you can pick this number to be whatever you want. Whichever you want. Provided that it's smaller than this number that you fix, because you start from sigma, so you have this number fixed. You can pick this, whatever you want between 0 and this number, 0 included. 0 included. And that's exactly what we want to do. So we start with sigma, such that the kind of result is true. No, I'm sorry. We start with sigma, for which we want to prove this kind of bound, which is the polynomial growth. Then from this sigma, we use the lemma to find the sigma tilde, such that these three are true. In particular, we find the sigma such that this number here, we want it to be 0. So the surface will have punctures instead of boundaries. In this case, then we have the result to hold true. And then we want a relation between n sigma of L and n sigma tilde of L. And of course, n sigma of L is smaller or equal than n sigma tilde of L. And because if you look at the definition, like you want the number of all the geodesics which have lengths smaller or equal than L. But then you also have this one. So this number is bounded by that one. And for sigma tilde, you have the Mirzakhani result. So you apply it to sigma tilde. And then you look here, and you have that one, you take the product of 1 over the length of, with respect to sigma tilde, and you can bound it with the same guy with respect to sigma this time. So this is how you get the polynomial growth for sigma.
You really need to go to Bardier algorithm.
Yes.
I would imagine that the proof of Lewanski just works in the case of algorithm. She cuts the surface in pieces and you can estimate some pieces.
So what you can do is you can modify the proof of Miyazaki
That's what I would do.
directly without using this lemma.
I believe so.
To be honest, I don't know. This is how they did it.
Okay.
We can ask this to get
I'm sorry?
We can ask this.
Yeah, you can ask again if it was easier, but I think this was easier.
Definitely.
Otherwise, they would have done the other way around, but I don't know what the proof of Miyazaki is.
So also just to note here, the epsilon is coming in this constant. So when you prove convergence, so back to the other question, if we're trying to prove convergence and you're setting on that constant out front, the zero epsilon would, as we vary out one per second and go into smaller epsilon, and then that can potentially
Yeah.
tend to be mass down. Yeah.
Okay, so what we have left, for example, the curve pants. The curve pants comes from something like that. They consider hyperbolic curve pants with length L1, L2, L3. And then, okay, let me do it with a different color. Take a point in here, and then you take a geodesic that goes to here, and you call this E1, 2. And then you take this one, and you call this E1, 1. And then they recover, so this is Bonn and Bardier together. They compute estimates for these two distances, which are functions of L1, L2, L3. And I would like to write some of them just to give a little bit the flavor of what happens, even if the computation is just too long, so we don't have the time to do it. So this one here, for example, in the case that all ni's are bigger or equal than epsilon, then this is bounded above by 4 times the natural log of 4 over epsilon plus 3 times log of 1 plus the exponent of L2 plus L3 minus L1 over 2. And it's bounded below by the logarithm of 1/2 hyperbolic sine, again, of L2 over 2 hyperbolic sine of L3 over 2 exponent of minus L1 over 2. So you have these kind of functions. Okay, let me write this here. This is bounded below by logarithm of 1 plus exponent of L3 minus L1 minus L2 divided by 2. And then again it's divided by 2. And this is logarithm of the same. By the same I mean this argument plus logarithm of 32 divided by epsilon squared. And this is in the case both L1 and L2 are greater than epsilon. So you have this kind of estimates. And moreover, there's a classical result that says that if the genus of your surface is at least 2, then the number of simple closed geodesics such that the length with respect to sigma is epsilon L. This is bounded by G minus 1 exponent of L plus 6. Sorry, can you read? Yeah. Okay, and now the trick is the following. So you want to have a bound how many times things can go wrong, right? And you reason like that. You take the interpretation of P, B, sigma, and P, anti sigma that we have seen before in terms of the C. So every time that you have a C connecting, you can create a pair of pens whose boundaries will be, for example, for this one, L1, L2, and the curve, right? The length of the simple representative of isomorphic class. And for D11, you will have L1 and gamma 1 and gamma 2 obtained that way. And because you have estimates on this length, then when you count the pair of pens in this way, you will also have estimates on the pair of pens that you recorded in that way. However, you want to bound the number of geodesics of this type. And here in these estimates, you only have a bound for the simple closed geodesics with bounded length, which is not enough because these are not closed. So what is the trick? Take your surface, and then you take the doubling of your surface. So you have minus here, plus, plus, plus. And this is your sigma with the pair of pens inside. Okay, so for example, this is a pair of pens. And then you take the doubling of sigma, which is recovered in this way. This sigma Miller, I don't know what to call it. And you will have a boundary here which is glued to that one. It's the doubling, and you don't have boundaries anymore. And then if you have a C here, you can double the C just like by mirroring it, and it becomes closed. And then you can say, okay, the number of these guys to each of these C's will give me a C in the doubling. And at that point will be a closed simple geodesic. And I know a bound for those ones. So I can use these estimates. But I will not have G anymore. Because if my surface has genus G and N boundaries, when I take the doubling, the genus of the doubling will have genus equal to 2G, because if I have genus here, I also have genus here, plus N minus 1, because each of the N's will give me a genus except the last one. The first you do and doesn't give you any genus, and every time that you do the other ones will give you one more genus. The audience is convinced. And then when you have g minus 1 exponent of something, now you will have instead 2g plus 1 minus 1 minus 1, which is 2g minus 2 plus n, which is beautiful, times exponent of something, which will be log of something. So the combinations are wrong, but you get that the exponent and the log cancels out, and you have some estimate here, which is a function of psi. And this is enough to bound, this is enough to give you the qi, this qi over here. So this is the idea of the proof. Okay. I already went over time because I wanted to stay 1 hour and a half. So I will just finish writing down the answers. Sorry, I covered this video. So let me write instead of these things. I wanted to write. And can result for sigma gn with n functions plus adaptation to boundaries of positive length. And instead of small pair of times, then I would write like estimates plus bound on the number of simple closed geodesics. Like bounded length. And this should be the view of that. Here it was until then. So easier of that contact sign. And then as the union and excision, circle in 1 and 2. Actually, the whole construction is done with this tilde, but at the end, like, there is a way to project and remove it, so I will just do it for simplicity without the tildes. because otherwise I have to write down the gluings for this particular case. And then the gluings are going to change, so it's an unnecessary complication for the purpose of this. So for the union, you do like that. You have E of sigma 1 union sigma 2. You can, because E is functor, then you have these natural maps Q1 and Q2. You go to E of sigma 1 and sigma 2. And then if you start from E of sigma 1 and E of sigma 2, you define U of F1 and F2. So F1 will be a continuous function on the Teichmüller of this one. F2 will be a continuous function on the Teichmüller of this one. You define this to be pullback of Q1 vector F1, Q2, F2. And then, for example, if you take sigma 1 to be the empty set, you plug it in here, this will give you K, and this will give you K. And then you look at here, you take the element 1, you pull back, you get the identity, you get 1, and then you have like Q2, pullback of Q2 of 2 times 1, which is exactly what you want. So it satisfies the vacuum axiom. And then the excision, if you glue together two elements, and then you want to evaluate sigma in the Teichmüller, this would be just F1 of sigma restricted to sigma 1, and F2 of sigma restricted to sigma 2. And this should go up. And the only missing thing is the admissibility initial data.
You can see that.
You don't see that. Is this better?
In the excision, I don't understand why is it continuous. There is a function on the complement, and then you glue them.
Yes, but you have the same sigma and then restricted to the two pieces. Right. The fission, you want to remove an embedded pair of pairs. So you start from a sigma, and then you have hyperbolic structure on the entire thing. And then what you do is just you restrict it to the two pieces separately. It's going to be continuous on the gluing.
Still a beam or the other way around?
No, that's the union. In the union, you start from two different pieces.
No, the excision.
Mm-hmm. Yeah. You start from sigma, and you want to take away a pair of pairs.
But it is the version from E of the pair. Okay.
You take the continuous functions on the pair of pens, that is F1, a continuous function on sigma minus the pair of pens, and you want a continuous function on the goal sigma. So you want to evaluate that thing on hyperbolic. You take the restrictions and you evaluate and remove. So sigma is an element on the Teichmüller space of capital C.
also think like in constants. You have one of sigma blah blah and you have two of sigma blah blah.
Yeah.
So that's fine.
Mhm. So actually your admissibility condition stays for A and E same. And the decay condition, you can make it a little bit simpler. Should write it here. So the B decay, for example, will transform into the soup sigma int of the percent as sigma. Why it's called B prime? I don't like this notation. How it is gamma. Minus still take the plus here. You multiply by dB of the curve times sigma. You wanted this to be bounded by some constant, that for each s and epsilon greater than 0, it exists such a constant and s greater than 0. So such that for each pair of times with boundaries V1, V, and gamma, plus, plus, minus, the soup of all these guys times this one is bounded by ms. And then if you take now the G-R recursion, the formula will also simplify a little bit. So now omega of sigma is a continuous function on Teichmüller, so I have to say what the evaluation with respect to sigma is. Then I take as before the sum over the b's. This stays the same, and also the sum over all the possible aeroplanes. But this time I can look at it in the other interpretation of P sigma that we've seen. So with this curve C. So C is now an element of C D1B, where D1B is just a set of curves that start from a point in the boundary D and go up to a point in the boundary D1 relative to the boundary, as before. And because the gluing is just a product, I can write D of aeroplane obtained by cutting along C. And you will have the length of D1, the length of D, and the length with respect to sigma, which is what I'm evaluating, the curve gamma C, times, because of the gluing, the surface sigma, but this time is cut along the curve obtained with C, so it's cut along gamma C. And I will evaluate this in sigma restricted to sigma cut in C. So this can possibly be not connected anymore, but it doesn't matter, just evaluate it on the multiple components, plus 1/2 of what you can guess see now it's a curve that leaves a point in the boundary of V1 and comes back in another different point, but also of V1. And here we'll have C of the pair of fence obtained acting along C, evaluated in LB, the length with respect to sigma of the first of the two boundaries, second, and then again times omega of gamma cut along C of sigma gamma C. It's just the same as here. And this concludes what I wanted to say.
Thanks to the speaker. Is there any question?
Or any question? Where is the S coming on the data area?
S?
Yeah, so there is.
Oh, yeah.
Ah.
Thank you.
Just vaguely, do you have examples or at least like intuitively what kind of data could be admissible data? Like, are there some cases in which, I don't know,
Yes.
the decay conditions will tell you kind of that these things could actually be constant maybe?
Yeah, actually, this is a very interesting question. So, one of the first examples that I should give you, like the first answer to this, I feel it should be the following. One of the, what is called the Miyazaki chain identities, it can be reinterpreted in the context of geometric recursion in the following way, answering your question. So it provides A, B, C, and D, such that with E, this E, so continuous function automatically, such that when you compute these quantities here, here you will get the function that identically 1. So somehow, the other time chain identities, but this is the topic of the next talk that Gaetan will here. Provides the initial data to have omega.
In that case, then if omega is going to be 1, probably A, B, C, and D are the things that are interesting to figure out what they mean.
Yeah, and A, B, and C, and D are quite non-trivial because they are given in terms of hyperbolic functions, in terms of L1 and 2 or 3.
A and D are 1 because
Right.
part of the are omega for
Yeah.
the pair of fence and the torus, but B and C are quite non-trivial. A combination of hyperbolic functions and logarithm.
They're quite specifically related to the geometry of
They also prove that 1 can be expressed like in a symmetric way. This way. Yeah. But yeah, Gaetan will say more about this one. And the second answer that I think I should give is that if you know something about the usual topological recursion, that generates like invariance of certain types, and there is a way of lifting topological recursion to geometric recursion. So topological recursion can give you several types of invariance, like certain Gomorrhian invariance with its numbers, polynomials related to knots, several things, and you can you have a notion of spectral curve that is used to generate this data, and then it was reformulated. Topological recursion was reformulated by Kontsevich and Seibelman in terms of ABCD topological recursion that is somehow in terms of like the structure of the recursion, it looks similar in the formula, but geometric recursion is much richer because really when you perform this recursion, you have all this extra data that you like kind of try to forget and some of them and keep the combinatorial structure, you get something that is similar to ABCD. So you can lift the spectral curve initial data to geometric recursion data, and this is actually what we are trying to do in some examples, like understand how it works. So it contains topological recursion in particular. But it's not exactly clear how, but somehow the principle is that if you integrate what you get here on the Teichmüller space, and then you take this Laplace transform, then you find the quantities that the topological recursion is giving you. So this is the relation between the two.